So we just introduced the Arrhenius equation and the idea that the rate constant has some information inside it that actually is physically relevant. The rate constant has size information inside it and also has motion information inside it. And also has this weird thing called activation energy inside it as well from an Arrhenius perspective. And so what we're going to do now with this video is we're going to look at just sort of addressing what we just introduced in terms of what components are inside K in a graphical way. And so the way that we do that is we use these things called potential energy reaction coordinate diagrams. All right, which sounds fancy and complicated, but we'll make it simple for you, okay? So just to review some ideas that we went over, and then also to take those ideas and relate them to these diagrams that we're going to eventually draw, okay? Reactions require collisions, all right? We said it a bunch. Make sure you understand the collisions have to have the correct energy and the correct orientation. Imagine that you have the correct orientation. Okay, let's focus on like the Arrhenius idea that there's some activation energy, which we just kind of defined as a symbol and didn't talk about. The necessary energy it takes for a reaction to progress, we can think of that as a hill, right? The size of that hill, that's our E sub A. So when we discussed activation energy last time, and we could use E sub small a or E sub big A, right? When we discussed activation energy last time, the connection I'm trying to make now and what it actually means is it's an amount of energy that has to be overcome, right? When things hit each other, it's the amount of energy that the collision has to have for us to take reactants and make them products, okay? Reactions could need multiple hills because of like multiple collisions that are necessary, right? Whenever there's multiple hills that are necessary, multiple collisions to occur, we say that the reaction has a certain mechanism that it follows, a certain mechanism that it follows, okay? And in our diagrams, we're going to refer to a reaction coordinate as reaction progress. The reaction coordinate is an actual coordinate that we could follow. It is an actual distance that we could follow. That's a little bit too complicated for this level of chemistry, and again, it's one of these things that we touch upon more in physical chemistry. So if reaction coordinate is kind of confusing, think about it as reaction progress, and that'll be good for your understanding, right? So that activation energy that we referenced last time, it's a hill. It's something that has to be overcome energetically to make the reaction proceed. So let's see what one of these looks like. Let's understand how to draw it, and then let's also make sure we understand how to pull important information off of the diagram itself. So let's do like a simple case to start with, a simple reaction. Let's say that we have A plus B making C, right? And again, these are stand-ins for different types of molecules that we might have, or different types of particles that you might see. When we think about what's actually happening from like a physical standpoint, again from the last video, it looks like there's an A floating around and it has a certain size. It looks like there's a B floating around and it has a certain size. And then these two things have to smack into each other. So somehow they have to collide. And when they collide, right, they make C. Now, if you think about what has to happen here, essentially what we have is A bonded to B. So that gives you a physical idea what C is, all right? A and B hit each other. They form a bond. We're going to call that new particle, that new molecule C, all right? But again, for the reaction to happen, these two have to hit each other in the correct spot, in the correct way, with the correct energy, okay? So if this is our example, and I'll just kind of write this up here as well. I think it's maybe more fruitful to think about it this way. So I'm going to write it up here. Think about this example where A and B have to hit each other, and then they form a new molecule, which we originally called C, and now we're going to call it A bonded to B, all right? We can monitor the energetics of that reaction. We can look at how much energy it takes for an A-B bond to form. And we can make a chart based off of that. And this is our potential energy reaction coordinate diagram, right? And the label, like what that name is, it tells you what goes on the y-axis and it tells you what goes on the x-axis. So what we're going to put here is we're going to put potential energy, and we're going to use units of kilojoules per mole. And we usually use joules or kilojoules per mole. It's a molar quantity. That's just important to kind of know from a mathematical standpoint eventually. Right here, we're going to say that this is the reaction coordinate, but remember, and this semester I'm fine with you actually labeling it like this, reaction coordinate, you can think about this as reaction progress. So in terms of what this axis is, on this side of the axis, we're going to have reactants, and on this side of the axis, we're going to have products. So reaction progress literally means that we're starting at the beginning where we have reactants, and then we're moving towards products, right? Well, the reactants themselves, they have a certain energy or a certain potential energy, and we like to indicate that with a line, okay? Now, these are where our reactants are energetically, and let's just kind of write them in there. So here's A, and here's B. Okay. Now to get a reaction to happen, they have to have the correct energy. Energies can be thought of as hills to overcome, all right? So what we're going to draw now is we're going to draw a hill, right? We're going to draw a hill. Notice what a hill means relative to this axis. The hill means that, oh, there's an energy barrier, there's an energy amount, there's more energy that's needed than the original energy just themselves to overcome. Just A by itself, B by itself, nothing would happen, but if I hit them together with the correct energy, I can get up and over that hill, okay? Now I'm gonna draw an example where, all right, our C, which is our A bonded to B, is at a lower energy. And we'll see that there's another example where it's at a higher energy than our reactants, and that should sort of start to kick in some ideas from last semester that you're familiar with, all right? But let's just draw this example right here. As a reaction progresses from reactants to products, all right, what we see is that there's a hill that needs to be overcome, all right? So from the standpoint of these guys, A and B, if you look here, they're at a certain energy, but to be able to get over this hill, there's a certain energy that has to be overcome, and that's our E sub A. So our activation energy is measured from where our reactants are to the maximum amount of energy that you have to get into those reactants for them to eventually fall to make products, okay? That's that special energy, and like I said, we call it the activation energy. Up here, if you think about it, this is the first instance where there's enough energy to make products. So imagine you don't have enough energy with a collision to actually get over the hill. What's gonna happen? A and B are going to bump into each other. Maybe they have this much energy, and what's going to happen, they're going to fall back down to A and B. Maybe they hit each other with more energy, they come here. Nope, they're still going to fall back down to A and B, all right? If they have enough energy to overcome the activation energy, if they have just E sub A, they still might fall back down this way, but it's the first instance where they could fall to the product side. That means that this position up here is really important. And what we do is we label that position as the transition state. That position right there at the top of the hill contains what's known as the transition state. The reason we call it transition state is it looks like it's kind of part this and part this. If you think about what's happening with this reaction, A and B have to form a bond. So up here in this transition state, which will be kind of right here, remember we're talking about right at the top of the hill, what this molecule looks like right here, right, is it looks like not separated A and B completely, not fully formed bond between A and B. It looks like, oh, a partially formed bond between A and B, right? It's the transition between the two. It looks like part reactant and part product. Again, an important point. When you're at the transition state, you could fall this way. When you're at the transition state, you could fall this way. But until you get this energy, if you just have lower energy, you could only ever fall back down to A and B, okay? There's one other important thing to kind of pick out in this diagram, and that is this difference between reactants and products, right? And this is the stuff that should hopefully sound a bit familiar. Well, this distance right here, right, looks like the difference in energy between reactants and products. And because most of our reactions are run at a constant pressure or isobaric situation, from last semester when we described reaction energies, we always called them reaction enthalpies, right? And that's what this is. This is delta H right here, okay? So delta H shows up again this semester, and it shows up directly on potential energy reaction coordinate diagrams, okay? The overall energy change in the reaction. In the case of this reaction, energy is released, right? Energy is released. The products have less energy than the reactants did. So this diagram right here, this is a diagram of an exothermic reaction, where delta H would be negative because energy went away, all right, and energy was released into the surroundings, okay? So key features of these diagrams: placement of reactants, placement of products, okay? Delta H, the difference between those two, same delta H as last semester. The new thing is, well, to even make this occur, to even get this delta H, there's an activation energy that has to be overcome. And as you're overcoming the activation energy, when you get to the top of that energetic hill, when you're at the very top, you're at the transition state, which looks like part reactant and part product, okay? I wanna do one more example quick. And I'm gonna write this one like a mechanism, and I'm gonna write it as like a multi-step reaction. So let's start by and then we're gonna draw in the transition states. We're gonna label all the important parts. Again, let's say we have this overall reaction that occurs, and the overall reaction that we're going to look at looks like A plus B plus C gives, and I'm just not gonna write it as a D, I'm gonna draw it as, oh, A and B have to be attached, and then B and C are attached with just single bonds, okay? Now what I'm gonna propose is a mechanism for this to occur, right? I'm gonna say that A and B come together to form AB. So see now how it's like multiple steps. AB isn't my product, that's not my overall product that I need something else to happen. Well, this AB, it can bump into a C, and we could finally make ABC. So overall, the reaction is this, and this would be the thing that we're looking at and analyzing from a kinetic standpoint, all right? But it's actually a two-step process. And you get a lot of this in organic chemistry where it's not always just a simple like one-step process. But wait a second, there's a collision here that has to occur, so there must be a hill to overcome. But you're not done yet. This thing that's made, it must collide with something else. And when it collides with this something else, there must be another hill that has to be overcome. Okay, so let's see how we can take this idea, draw a potential energy reaction coordinate diagram, and label all the important parts of it, okay? So with this in mind, and yeah, I'll just leave this here for now. Let's draw the potential energy reaction coordinate diagram. So I'm gonna put potential energy here. Again, I'm gonna pick like kilojoules per mole as the unit, right? Here I'm gonna put reaction progress. You could label this reaction coordinate if you want. That'll be fine as well. Either way is gonna work. Let's say that we have A and B and C here. Okay, A and B and C there. And let's say for this instance that we end up with like A bonded to B, bonded to C there, right? So separate A, B, C here. Oh yep, those are my reactants. Bonded A, B, C there in terms of the energy. Yep, that's my product that I'm making. So what happens in the middle as the reaction progresses? Well, the way that we set it up with this mechanism is first A and B hit each other and you make A, B, right? That itself has a certain activation energy, okay? That would then lead to a new state, and that state then would have A, B, and C with it. So let's write that in there. Now when I have AB plus C, that final collision could happen. And when that final collision happens, right, then I can get to my products where A, B, and C are all attached to each other. Right? One more time just to make sure you understand. This is saying A plus B plus C are all separate. A collision occurs, and I make A dash B, which means that they're bonded. That's a single bond there. C is still floating around by itself, but to get to the final product, C has to hit into A bonded to B. In the correct way, it has to hit B and not A. But it goes over another hump, and then you have your final result. Right? A bonded to B, bonded to C. Right? So pause the video now. Try to write in, or not now, but after I explain what I want you to do next. Try to write in what this transition state looks like here. And then also try to write in what this transition state looks like here. Okay, so if you look at what has to happen at the transition state, oh, well, A and B are forming the bond here. So this transition state looks like, oh, A and B are starting to form a bond. And so we use dashes or dots to say it's not a fully bond. You can't really see that, sorry. It's not a fully formed bond yet, but it's definitely starting to. And that's the first activation energy we have that could possibly lead to making this sort of part of the process occur. C is still off by itself, right? To fall down this hill now, you've made the bond fully. Oh, so then this guy here must look like A and B are fully formed, but C is just starting to form. And then you fall down into A bonded to B bonded to C, right? This region right here, or this species right here, we call this an intermediate. Right, we call it an intermediate because you're not done yet. It's like an intermediate step. It's something that you make along the way that's used up again to finally get to your products. Right. Again, to make sure you're understanding, I'm going to ask something, pause after the question. Is this reaction endothermic or exothermic? So hopefully you can see that this reaction is endothermic. If you look at the reaction and you look at the distance between, right, your reaction energy and your product energy, you gained energy going to the product side. You started here, you went up in energy, energy was sucked into the system. It's an endothermic process, right? Can you find the activation energies? There's two, because there's two steps. The first activation energy is here. The second activation energy is here. Okay. So hopefully you can see that as well. Right. There's one more thing I want to talk about real quickly, and that's catalysis and a catalyst. And a catalyst is something you've heard of just from your experiences in the real world. We're going to start by getting a definition down for what a catalyst is, and then we're going to talk about how catalysts affect potential energy reaction coordinate diagrams. So a catalyst is a species in a reaction that is not consumed but lowers the activation energy for a reaction. The purpose of the catalyst is to lower the activation energy. Now, technically, the way I like to think about it, even though this is a fine definition, if I ask you for a definition, definitely give this. And on standardized exams, this is a good definition as well. It doesn't like lower the activation energy. It effectively does that. It provides a different pathway that has a lower activation energy. Okay, so you see what I mean. So let's look at a reaction. This will be the last thing for this video. I really like my green. Again, let's draw potential energy in kilojoules per mole, and reaction coordinate here, or reaction progress. All right. And let's say we have an exothermic reaction. And I'm just gonna write in R for reactants and P for products now. And I can see it's exothermic because we're losing energy, right? Well, what happens if we have a really steep activation energy? Again, we can note that the activation energy is this distance right here. That's our activation energy. What we do with catalysis or with a catalyst is we put something else in there for the reactants to collide with. Collision is still required. All the mechanistic ideas are still needed, but the catalyst makes the collision occur easier. It orients things correctly. All those things that we talked about with K, the catalyst helps at. Provides a bigger surface, etc. So what K will do is it'll respond to a different pathway through here. The catalyzed pathway might have this activation energy. Now, if you look at the red hill versus the black hill, right, what you'll see is that the black hill, which comes about because I put a catalyst in there, right, has a lower activation energy. So when the reaction progresses and it has a choice to make, do I go over the big hill or do I go over the small hill? It's going to go over the small hill. So effectively what happens is the catalyst has lowered E sub A. It has lowered the activation energy. Again, be able to look at this diagram, see that delta H is exothermic, get used to analyzing these diagrams. Just to recap, all right, potential energy reaction coordinate diagrams come from this understanding of activation energy that's necessary in the Arrhenius equation for K, all right? These diagrams can monitor the course of a reaction and can talk about the energetics necessary to complete individual steps, which are these activation energies, or the total energetics of the situation, which is the delta H, which is the difference between the reactant and product energies themselves, all right? As we go through a reaction, we hit transition states, which occur at tops of the hills, all right? They look like kind of both ends of their hill, all right? They could fall either way, all right? And their structure kind of makes sense in terms of what it looks like. And then also, if it's a multi-step process, if it's a mechanism, all right, we have these things called intermediates that are sandwiched between hills, okay? So try to digest this, and then again, as always, email me if you have any questions.